B people like to get ahead. All right. 1.4, example 15. We are on part E, and we're approaching 0, and we got trig. Okay, so we memorized 2 of them yesterday, right? The limit as x goes to 0 of 1 minus cosine of x over x is what? 0, co. And then the limit as x goes to 0 of sine of x over x is 1. Why? 1. That doesn't quite work. But remember, there is a way, right? Sine and cosine, the 1 and the 0. So whatever. But never not first, direct sub. So let's do it. We have an angle of 3x and an angle of 4x. So of course, if you plug in a 0, you're first going to multiply the 3 and the 4 by 0. So you basically have tangent of 0 over sine of 0. Can you walk away there? Is that a numeric answer? Tangent of 0 over sine of 0? No. Both of them are defined at 0, but it's still not a numeric answer because you get 0 over 0, right? You get a 0 in the denominator and in the numerator, so it's not undefined either. Any ideas? We saw a tangent yesterday. What did we do? Very good. Tangent of 3x, we said, behaves like sine of x near 0. So in this case, let's go ahead and write it as sine over cosine. Sine of 3x. All right, you know what? We don't even need to put it in terms of sine of x, do we? If we, let's come back. Did we even summarize it? I don't know if I wrote it anywhere. I wrote it somewhere, maybe not. Here we go. The limit, let's do it right here. The limit as x goes to 0 of tangent of mx over mx is the same as the limit as x goes to 0 of mx over tangent of mx. And of course, you could substitute sine in for tangent, right? It's equal to what? 1. Okay, so we don't have to put tangent now in terms of sine if we're approaching 0.
So we just multiply by like...
Yes, so let's go ahead and we need to create what we know to be 1. So I have a tangent of 3x here, and I have a sine of 4x there. So what I'm doing is I'm just splitting them up, giving them their own factor. Now, in order to call each of those factors 1, it needs to be tangent of 3x over what? 3x. So even though we're missing an x as well, we can go ahead and multiply by 3x in the bottom, creating what we need. Yeah, as long as we put another factor of 3x in the numerator somewhere else in that term, which I'm going to put it back here. Absolutely. We know that they work for reciprocals as well, so if we had a 4x in the top here, which I'll put 1. It's going to be 0? Well, you're going to get 0 over 0 down there, and we'll take care of that too. So, all right, so now that we've created what we needed by multiplying cleverly, remember, by a clever form of 1, we can evaluate it, and the limit can go away. So the first one, of course, goes to 1. The second one, of course, also goes to 1. Now, if you use direct substitution on the third one, as Megan noticed, we get 3 times 0 over 4 times 0. We have 0 over 0. But notice this goes back to the very first method that we learned for evaluating. Who's the bad guy now? The x's. And it's already factored out. So what happens to the bad guy? They divide out. Yeah, they divide out. And we're left with 3/4. Yeah. This last piece here, 3x over 4x, would graph just like the horizontal line, y equals 3/4, except it's going to have a hole at the order pair 0, 3/4. Okay, so the extra x's that we picked up end up dividing out. And now, of course, we're left with just 3/4. Now, double K was quick yesterday to summarize. If we had like sine of 5x over 4x, as x goes to 0, it was 5 over 4. And you can do a lot of summarizing with a lot of these things, so long as you keep them all straight in the end. We ended up with 3/4 as an answer. Was there a 3/4 originally visible anywhere in the problem? Yeah, it was slightly. It was the coefficient of your angles in your trig functions, sine and cosine. Is that a coinky-dink? No. Now, I'm not going to prove it. We proved it yesterday. All you have to do is just plug in an a and a b, and you'll end up with a over b. Yeah? No, and that's what I'm getting at here. We did it once. We can extract the general idea, and then we don't have to do this anymore in the future. Right. So if you ever see the limit as x goes to 0 of tangent of 3x over sine of 4x, it's always going to be 3/4 every time. But it doesn't have to be 3/4 either, right? It could be any number. Yes. Any additions?
So the reciprocals of tangent and sine, would that still work like cotangent over cosine?
Ooh, wow. You are getting, that's where we're heading. We're going there. We are going there, Eugene. But before we go there, let's make one more broad summary about this. Because tangents and sines act the same towards 0, this could be any ratio of tangent to sine. So it could be tangent to tangent. It could be sine over sine. It could be tangent over sine like it is, or it could be sine over tangent. As long as it's tangents and sines, and that's it, it will always just be, as you're approaching 0, the quotient of the angles. Good. Now, speaking, yes, Frenchie.
How did we multiply by clever form of 1?
How did we?
Yes.
Well, notice this is one big term, so the associative and commutative property of multiplication say we can multiply and divide any of these in any order. I color-coded it, so I divided by 3x here, and I multiplied by 3x over here. But because it's all the same term, this 3x and this 3x essentially divide out. 3x divided by 3x is 1. 4x in green divided by 4x is 1. So we're multiplying by two different clever forms of 1, but we're cleverly reassociating it. One with what we need to make it 1, and then the other one just ends up back here as extra, and we deal with it later. Okay, so that's why it works. So let's throw in this other one right here real quick before we move on, a bonus one. And bonus as in like extra problem that we get to enjoy, not extra points, Clay Tillman, right? Okay, and they showed me a picture of him last period. He's at the core. He's bald. It's pretty shiny. Yeah, it's pretty shiny. So it should blow up the internet soon. All right. What about the limit as x goes to 0 of sine of 12x over sine of 6x? Dang it. 2. Without the sign there, you mean? It could just be sine of 12x over 6x? Yeah, well, let's see. Is that what we summarized yesterday? Sine of 12x all over 6x. We said yesterday that was also 12/6, which is also 2. Yeah. Yeah. Good. And it works with tangents as well. So any ratio of tangents and sines, and of course what we saw yesterday. Now, Eugene, I don't know if you're looking at letter F or that was just a natural evolution of this idea, but what about the reciprocals? Well, we have the limit as x goes to 0 now of cotangent of 11x over cosecant of 25x. Never not first. I'm never going to let you get away with not plugging in. What is cotangent of 0? It's DNE because it's some type of infinity. It actually has different behaviors on either side of 0. And what about cosecant? Yeah, it's also infinity. Yeah, because remember, it's the graph of sine, so it's actually going to go down to negative infinity on this side and positive on that side. So what is infinity over infinity? Is it 1? No, it's indeterminate form, right? Because infinity over infinity is just the reciprocal of 0 over 0. So both of those are your indeterminate forms. Now, how are we going to do it? Well, if we were going to actually work it out, my first step using identities would be to bring the cosecant to the top and call it sine of 25x, and to bring the cotangent to the denominator and call it tangent, because it's the reciprocal. So we would end up with sine of 25x over tangent of 11x, which of course, based upon the previous rule, would give us what, Eugene? 25/11. Good. So it does work. It does work for the reciprocals. So that's a whole broad sort of ideas to kind of absorb. Any ratios of tangents to sines, or sines to sines, or sines to tangents, or sines to sines, or tangents to tangents, or now they're reciprocals. But with the reciprocals, it's not the visual ratio that you see of the angles, it's the reciprocal. Okay? Flip it. Now, of course, if you ever forgot, you could work it out. You could use the identities, and you could do exactly what we did right here, create what you need. Okay? All right, moving right along then, letter G. What we got? 14/9? See, once you get lured into that rule, then I can throw in like this. You're approaching 0. You see 14/9? It'd be right there. Answer choice A. 14/9. Ooh, that looks good. Huh. It looks good. 9/14 also looks good. But what do you never not do first? Plug in a 0. Well, in this case, plug in a 0. You don't always plug in 0, right? Because if we're approaching 10, you plug in 10. Good. All right. What's cosine of 0? 1. Oh, is that going to be an indeterminate form? No, because it's either 0, 0, or infinity over infinity. So I think we're going to get an answer. What's cosecant of 0? Is it 0? It's D and E because it's some type of infinity. What? So we get 1 over plus or minus infinity. It approaches what? 0. Very good. How do you know 1 over infinity is 0? Very good. Because when we say infinity, we mean approaching infinity, right? Because we're approaching 0. So if the top is always a 1, the bottom gets bigger and bigger and bigger and bigger. Whether it's negative or positive, the ratio is getting smaller and smaller and smaller. It's approaching 0. So direct substitution works. Now, if you don't like that, if you want to use a little bit of a trig manipulation using an identity, that's what identities are for, right? Keep the cosine of 14x in the top, and what can we do with the cosecant in the bottom? Yeah, bring it to the top and call it sine of 9x. Now direct substitution. Cosine of 0 is 1. Sine of 0 is 0. What's 1 times 0? Yeah. Yes. Do we get the same answer? Yeah, but it requires actually a little bit less analysis. It's more straightforward. It's just a computation. Is that going to be a yellow pizza? Oh, cheese. Just slice of cheese. Okay. That looks like crust, though. Oh, that is the cheese. So that's the top. All the red sauce is underneath.
Well, I'm gonna add it now.
Oh, okay. All right. I'm getting hungry now. I wanted to play basketball, and now I'm getting hungry. Letter H. You do it. Letter H. 7 over pi, right? That's answer choice A, 7 over pi. Yeah, it's answer choice A, but yeah. By the way, sometimes A could be the right answer.
You should just put like
7?
7.
Abraham Lincoln. You know what I could do? All the AP multiple choice questions now have 4 selections, A, B, C, and D only on the AP exam, and I have choice E. So what I could do is I could keep choice E, and on every single one of them put Abraham Lincoln. Somebody's name, yeah. And then when you're not suspecting it, I will write a question so that the answer is actually a string of variables that spells out that person's name, and you'll get it wrong. Yeah, that's a lot of work. I'll do that this Labor Day weekend because I got nothing else to do. I don't float the river. The river floats me. I snorkel. Yeah. All right. Let's use direct substitution, shall we? Yeah? Cosecant of 0. D and E. It's the third time we've seen it because it's some type of infinity. So it's better to put, you can put plus or minus if you want. And then in the bottom, lunch? Yeah, now what's infinity over 0? Is that indeterminate? You either bring the 0 to the top and make it infinity times infinity, or you bring the infinity to the bottom and make it 1 over 0 times 0. Either way, it's some type of infinity. It's D and E. Good. All right. We'll pick up with I when you get back. Not with me, with I.